Let me start off by just sort of reviewing some concepts that everybody is supposed to know. And that has to do with the circle. Trigonometry has to do more with triangles, but we're going to start with a circle. So this circle, and these are terms that everybody is supposed to know, but I just thought I'd review them anyway. The circle has a center at O, so you can see what I'm pointing to there as the center of the circle. And you see some lines going from the center out to the edge of the circle. So there's OA, there's OB, and there's OC. We call those radii. AB is a diameter, so if you go from one end of the circle to the other end of the circle through the center, then what you have is a diameter. And AC is the circumference, is this AC going from A to C is one part of the whole circumference, which is called an arc, right? So that red line that you can see there, that's referred to as an arc, right? So it extends from the endpoints of those two radii. And OAC, so this whole section right inside here, all of that is referred to as a sector of the circle. In fact, I don't really need you to see that all. Let me just erase that. So the arc is just the length along from A to C, but the whole sort of area here inside of that little sort of slice of the pie is referred to as a sector. The angle at the center, which is labeled as theta, that's a sector angle or a central angle, right? We can either call it a central angle or a sector angle. Both terms are interchangeable. So I'm just sort of going over some terms that represent the various parts of a circle that has a radius or radii, right? And an arc and an angle at the center that we call the angle that subtends the arc, right? So this angle at the center, this angle that's measured, that we're calling theta, is what's called subtending this arc. That's the word that we use. That's the fancy word that we use right there. Okay, so there is a relationship between the size of this angle and the length of this arc. I mean, that hopefully is obvious. The bigger this angle is the longer this arc tends to be. Okay, bigger angle, longer arc. Smaller angle, shorter arc. Okay, now, why we're going through all of that is because we're going to introduce you to a different way of measuring the angle at the center of a circle. You're used to something called degrees, and in a circle, normally we have 360 degrees. But we're going to define this angle that's at the center of the circle that subtends this arc in a different way. We're going to say that when this arc, right, this distance here A, right, you can see the distance I'm pointing to, when that distance is the same as the radius of the circle, so this arc that you have along the edge in blue is the same length, the same distance as the radius of the circle, we're going to call this angle at the center 1 radian. So what we're really doing is we're measuring the size of the angle in terms of the number of the size of this distance along the edge of the circle. And every time we have another radius, we're going to call this a radian. So what you're going to see along the side here is it says that the radian measure of an angle is defined as the length of the arc that subtends the angle divided by the radius of the circle. So if I have two radius lengths here, let's say that I were to, let's say this R here is, for instance, 3 centimeters. So if I go 3 centimeters along the edge here, that will be 1 radian. If I were to go 6 centimeters, that's 2 radians because that's 2 radius or 2 radii, I guess, right? So you're measuring the angle at the center in terms of the length of this arc and asking how many radii am I going around the edge of this circle, right? If I go 1 radius, then that's 1 radian. If I go 2 radii, then that's 2 radians, and so on and so forth. Okay, so let's see now. Somebody has a question about that. Please go ahead, Quinn. Mm-hmm. Correct. Yep. Yep. So obviously, and that's exactly right. So obviously, so what Quinn is asking is, because I have to repeat the question, is if the angle at the center is somehow related to the length of the arc, and in terms of the number of radiuses or radii, I guess is the plural, the number of radiuses that you're measuring. So let me change the color of this a bit so that I can make that clear, right? So this R represents one the length of the radius. So this arc, excuse me, is the length of one radius right now. But what if I decided to make it 2 radii, right? Then it means that the angle at the center would now be 2 radians, right? And if I were to make that bigger, and now I'm covering 3 radii, then it would be 3 radians, right? So the bigger the angle is, the more radiuses, or radii, I think is the plural, that you're going to be covering, and every additional radius that you have to cover is another radian. Okay, let's just make sure everybody follows what I just said, right? The length of the arc is related to the size of the angle. And as that angle causes you to have an arc which is 1 radius long, then it's called a radian. Okay? All right, so that's what this thing is on the saying, that this angle is equal to the A, the length of the arc, divided by the radius. So if you have, an arc which is 2 radiuses long, then the angle is going to be 2 radians, and so on and so forth. Now, bear in mind, go back and think about the circumference of a circle. The circumference of a circle is 2 pi r. We learned that from elementary school. So it means that if I were to do one complete revolution, we can do the math on the side here. We're going to take that length of the circumference, which is 2 pi r, and divide it by the number of radiuses, or radii, which would give us, for a full circle, 2 pi radians. So that's really what the main thing is that we want to understand here, that one complete revolution is measured in terms of 2 pi radians. So we used to use 360 degrees, right? 360 degrees would be one full revolution. But now we're saying that another way, if we're measuring it, is in terms of radians. And if we did a full circle, which is 2 pi r, that's what a circumference is. And that's equivalent to 2 pi radians. So it's now going to be possible for us to find a relationship between radians and degrees, because 2 pi radians is equal to 360 degrees. And that's the most important thing that I want you to get from what I've done so far. What we used to call 360 degrees is what we're now calling 2 pi radians. So one is measured in degrees, one is measured in radians, and they're equivalent. 2 pi in one system is equivalent to 360 degrees in the other. What do I mean by 2 pi? 2 times whatever the value of pi is, right? We know that pi is, what is it, 3.142, whatever it is. Well, 2 times that in radians is what we're calling 360 degrees. Okay, hopefully that is good so far. So let's continue. So the thing I just said a few minutes ago is what this first line is saying, that 2 pi radians is equal to 360 degrees. And obviously it works the other way as well, that 360 degrees is equal to 2 pi radians. Now, what I'm going to get you to focus on is these two things right here. And you might want to write them down or circle them. I have all of this, as usual, on the Math Video Library. If you downloaded that ahead of time, then you could use that to make notes as we go along. I want you to pay attention to the thing I just circled, the 180 over pi and the pi over 180, because those two things are what you can use to go from one system to the other. So it's almost like going between English and French, or between French and English. How do I convert, how do I translate from one system to another? Well, you're either going to use 180 over pi, or you're going to use pi over 180. So if I want to go from degrees to radians, and the thing is, degrees is what I'm accustomed to, so I want to go from an angle in degrees and I want to convert that to radians. Then I'm going to multiply by the pi over 180. That's if I want to go from degrees to radians, right? And I'll give you an example of that in a minute. If I wanted to go the other way, if I had to start off with radians and I wanted to go to degrees, then I'm going to take the reciprocal of that, which is I'm going to multiply by 180 over pi. So it's probably not a bad idea for you to memorize those two things as we go along for you to make the transition from one to another. So if I start off with degrees and I want to end up with radians, I'm going to multiply my degrees by pi over 180. If I start off with radians and I want to go to degrees, I'm going to multiply by 180 over pi. I want you to notice that that pi, when you start doing some examples, will probably be left as part of your answer, meaning you're going to end up with an answer which is a multiple of pi. When I give you the first example, you'll see what I mean by that. Okay, so I'm going to go to my next page and my first translation or my first sort of conversion of one to the other. So it says determine an exact and approximate radian measure to the nearest hundredth for an angle of 30 degrees. Let me take you back a second. I'm starting off with degrees and I want to go to radians. I said I'm supposed to multiply by pi over 180. So I'm going to take my 30 degrees. I'm going to multiply it by pi over 180. Now, this is just a simple sort of fraction calculation. So it's going to be 30 times pi over 180. I just simply multiply the 30 times the pi to 1 times the 180. And of course, I can cancel this down. I can reduce this down. 30 goes in, and you can double check this for yourself. 30 goes into 180. Actually, let me cross that out with a different color. 30 goes into 180 6 times. So what? Oh, I'm not sure why I'm using yellow. Let's try that again. So what I'm going to end up with is pi over 6. So not 6, Mohammed, but pi over 6, because the numerator was 30 and the denominator is 180. So it means that it's going to be less than pi. It's going to be pi divided by 6. Does that make sense, Mohammed? Or does that make sense? Just want to make sure that's clear. Mohammed, are you good with that? Okay, great. So notice that I didn't leave it in a decimal format. And many times when you're doing this, I actually want you to work it out so that it's a multiple of pi. And notice something else. I don't put the word radians beside it, because when you see an angle of pi over 6, it's assumed to be in radians. Normally, when you have an angle in degrees, you have to put a little degree sign there to show that it's degrees. Well, in this case, we're going to say that the answer is radians because there are no units, right? So you can leave the units off. And once it has a pi in it, then it's assumed that it's in radians. Now, what does this mean in terms of, it says an exact and approximate radian measure. So we can convert that into an approximate by just simply doing a calculation. So what we're going to do is we're going to take the pi, right? And then divide that by 6. And put that in decimal form. They asked us to the nearest 100, so that means 0, and you can put this on your calculator as well, 0.52. And because it's not clear what this is in, because I don't have the pi as a multiple, I'm going to put the word RAD beside it to suggest that it's radians. Okay? All right, so there's our first calculation. There's the first time that we're converting from degrees, the normal thing that we were using way back in probably elementary school, to this new system that we're calling radians. Okay, so let's move on to having to go the other way. Determine the degree measure. So now we're taking a radian measure and converting it to degrees. It asks you for to the nearest tenth for each radian measure, right? So determine the degree measure to the nearest tenth for each radian. So these are both in radians, right? The pi over 4 is in radians, the 5.86 is in radians. What we're trying to do is convert these into degrees. So let me take you back again. This says, if I start off with radians and I want to get to degrees, I'm going to take 180 over pi and multiply that by the result that I'm trying to get. Not the result, from the angle that I got in radians. So 180 over pi. So I'm going to take the pi over 4 and multiply that by 180 over pi. Well, look at that. The pi's are going to cancel out. And what I'm left with is 180 divided by 4. And of course, 180 divided by 2 is 90. 90 divided by 2 is 45. That's actually 45 degrees. So pi over 4 is equivalent to 45 degrees. Now, this one doesn't need to be rounded because it's obviously exactly 45 degrees, right? The fact that this had a multiple of pi in it already means that this angle is just going to be an exact number of 45 degrees. But what about the 5.86, right? Yes, you're right, Cosine. Cosine has 45 degrees. Well done. What about the 5.86? So I'm going to do the same thing again. This was part A. This is part B. I'm going to take my 5.86 and I'm going to multiply it by 180 over pi. Now, there is no pi to cancel here. We don't have that this time. So we're just going to have to do a straight up calculation by taking the 5.86 and multiplying that by 180 and then dividing that by pi. What are you getting when you do that? How many degrees is that? You can put that in the chat. Let me see what people are coming up with when they do that on their own. Right? Okay, it did say to the nearest tenth. So to be accurate, we should actually put 335.8 to the nearest tenth. And of course, I'm going to put my degree sign in this time, right? Everybody got the same question. Everybody got the same answer. And I'm going to check in with the room from time to time. That's something I'm still going to be doing. Alexa, are you there with us? You almost anticipated I was going to be asking that. There you go. Yeah, good. All right, so everybody got the same thing? Great. And it's very simple. So as long as you know which one to multiply by, it's easy to convert from one to the other. If you want it in degrees, then you multiply by 180 over pi. If you want it in radians, you multiply by pi over 180, right? 360 degrees is the same thing as 2 pi, and that's what sets up those two conversion factors. Okay, simple enough, hopefully. Now, one of the things about measuring the angle in radians is it makes it very easy to find the length of the arc, because the arc length, the simple calculation for arc length is to multiply the angle in radians. If it's in radians, multiply that angle excuse me, by the radius. It's really that simple. Now, if this wasn't in radians, you'd have more work to do, right? The length of the arc, if it's the angle is in radians, means you just have to multiply, because of the fact that the arc length in radians also incorporates the pi in it already and all of that, you just have to multiply those two things together. So let's look at this question. Suzette chooses to ride a camel to ride on a carousel. The camel is located 9 meters from the center of the carousel. So that 9 would suggest that that would be the radius. If the carousel turns to an angle of 5 pi over 6 radians, determine the length of the arc traveled by the camel to the nearest tenth of a meter. So a quick diagram of that would be this. She is 9 meters from the center. That's where the camel is. And the angle that she is turning through is the 5 pi over 6. So what we're asking is, what's that distance that she's traveling through? How far is that? Well, according to this calculation, all we need to do is to take the angle of 5 pi over 6 and multiply it by 9. It's really that simple, right? Just simply multiply those two things together. Well, let's see if we can do a little math here. Let me see if I can do this without too much pain. I divide that by 3, which gives me 2. That gives me 3. So I'm getting 15 pi over 2. Now, what do you think the units need to be for this? Did I do that right, by the way? 5, 2, 15 pi. Yeah, I think I did. Yeah. What units do you think would make sense in this case? Right? It would be in meters, absolutely, because they gave us the original thing in meters. It was 9 meters in that case, so that's 9 meters. Now, if we had to simply turn that into, it said to the nearest tenth of a meter, and all I need to do is to just do the math on that, which is to take 15, multiply it by pi. Oh, sorry, I did that wrong. I'm doing it on my virtual calculator here. 15 times pi, and then divide that by 2. And what are you getting when you do that? Let me go to the room here and see if I can get some help with that. Okay, so Alexander's answer, 23. Well, okay, good. Good stuff. 23.6 sounds good. Thank you all very much for your responses. And of course, that's also in meters. I'm going to put approximately here because whereas the 15 pi over 2 is an exact answer, the 23.6 meters is an approximate answer. Okay, let's move on. So that's a simple use of the radian measure. If it's in radians, if it's not in radians, then we have to use a different strategy. But if it's in radians, then you can just simply multiply those two things together and you get the length of the arc. It's very simple. All right, one more thing we have to do with this, and that's something called angular velocity. Let me explain what that is. You may have done this in physics before. As something revolves, if you think of a hard drive, those of you who are into computers, not the more sort of modern SSD drives, solid state drives, but the older hard drives, a lot of computers still have the older hard drives. They rotate, right? There's a spinning platter. There's a needle that moves across that platter that is reading various data on that spinning drive. Or think of an engine in a car. Think of you may have heard of vinyl records. Not sure if you have, but maybe your parents can tell you what that is, right? Things that turn, right, that constantly rotate, have what's called an angular velocity, which is how many degrees they have gone through for a certain amount of time. That's what angular velocity is. So they've revolved through, let's say, 20 degrees per second. I'm just using that as an example. Well, we can do that for anything, but we can do it in radians and we can do it in degrees. So we're going to do that right now. So a rotating object is going at a rate, and they use a hard disk as an example, of 7,200 revolutions per minute. And all that means is that every single minute, that hard disk, the platter inside the hard disk, rotates 72,000 times. It's really that simple, right? That's what the RPM is, right? That's the revolutions per minute, right? So it's pretty fast, right? Just as how an engine, if you look at it, most cars have an indicator in there, a gauge in there that tells you the revolutions per minute for that engine. Most of you have probably seen that already. It's the same thing here, right? So 7,200 RPM is the rate at which this thing is turning. So what we're asking is, what's the angular velocity in degrees per second? So remember, every time you turn, you go through 360 degrees. So if you're going to turn 7,200 times, then the angular velocity, it's a pretty big number, is going to be equal to that 7,200 multiplied by 360, because that's the amount of degrees that one revolution would cover. So if I'm going to do that 7,200 times, then I'm going to cover that many degrees. And now I have to put that over the number that they want it to be, which is in seconds. So it says per second. I'm going to put that over 60 seconds because that's per minute. So since this takes place in a minute and I want this in degrees per second, I put the number of degrees it's going to revolve through on top, and the number of seconds it's going to take to do that. Okay? I want to make sure that people are understanding me so far. Natasha, how about you? Does that calculation so far make sense before we actually, okay. So why don't we go ahead and do that, right? I mean, this is not something I expect anybody to do in their head. Give me what that is in degrees per second. All right, so Alexander's worked so to, and that's you've already divided by 6, Alexander, by the way, because I haven't done the calculation yet. He has, okay. So 432,000 432,000. And the unit is degrees per second. Okay? So that's the calculation for angular velocity for part A. But how about part B? How does this calculation change? You got 43. Oh, okay then. Who is right, who is wrong? So it's 43,000. Okay. Alexander, are you off by a zero there? Okay, all right, so I'll change it. Okay. All right, we all make mistakes. That's no big deal. We'll just quickly make a change here. So I'm getting 43,200. And I'm glad everybody else did this for themselves rather than just depending on one person to do it. So 43,200 degrees per second. Okay, so how does this calculation change if I'm doing this in radians per second? What's the one thing that I need to change for the same calculation, but for me to get this for radians per second? Somebody can help me out with that. So Hussein is saying 2 pi r instead of 360. I absolutely agree. So we're going to do that. So it's the same angular velocity calculation, but now same 7,200, because that's the rate at which it's spinning. But instead of 360, we're going to put 2 pi instead. And we're not going to put the word radians. It's just 2 pi, right? So 360 is 2 pi radians, and we're still putting that over 60, right? So we could give an exact answer for this as well as we could give this in decimals. But let's start off with, go ahead and do this now. So 7,200 times 2 pi divided by 60. Let me see if I can get somebody to give me that answer. Let me just change my layout here so I can see more people. I have more that I can call on. There we go. All right. So how about I ask Brannon for that answer? Brannon, can you give me an answer to that question, please? Can you just go through the calculation? Leave the pi in it for now, right? So it's some multiple of pi instead. Brannon, can you help me out with that, please? Brannon, are you there? Where's Brannon? Where is Brannon? Brannon, you're supposed to be with us. Where are you, Brannon? Come on, Brannon. Calling on you. Where are you? Lynette, go ahead, please. Correct. So the answer, so Lynette's question was, we're just solving for angular velocity. But the answer obviously needs to be in radians per second this time. Okay, so Brannon, I'm still looking for you. Where are you? Okay, can't find Brannon. Where is Brannon? Okay, I'll go to somebody else for now. Davina, are you with us? Davina, are you there? Where's Davina? Davina, perfect. Davina, could you do the math on that for us, please, and give us that answer, but leave it in terms of pi. So really what I'm asking you for is some multiple of pi. We can put that into decimals afterwards. Does that make sense, what I just asked you to do, Davina? So don't leave the pi in the answer. So you're saying 240 pi, and everybody else agrees with that answer, by the way? Quinn says yes, and anybody else on the same page as Davina on that one? Donna says yes. Okay, I'm going to write that down then. So 240 pi. And again, the angle this time, so the answer this time is going to be in radians per second. So that's the difference. All right, the difference is in terms of, Brannon, we were just calling for you. Where were you? We were just asking for you, asking you to help us out with something. Are you with us now, Brannon? I see that you just rejoined us. Are you there? Yeah. Messages weren't sending. Okay. Oh, okay. Not sure why that is. Anyway, so Brandon, does that calculation make sense? How did you get that answer? So Sindhuja, so they're just asking how we got that answer. Take the 7,200, multiply it by 2, and divide it by 60. Don't do anything with the pi yet. We can do that on the next line. leave the pi as a factor. Okay, Seduja? So you take the 7200, and by the way, I'm assuming the answer is right. Okay. Take the 7200, multiply it by the 2. Yes, Queen, go ahead. Good, good, Seduja, great. Queen, you have a question. Please go ahead. Good, good. Okay, so Quinn is asking, and again, repeating your question so that when I record it, people can know what it is I'm responding to. What do these numbers actually mean when it says, for instance, 43,200 degrees per second and 240 pi radians per second? What does that actually mean? It means the following, that every second, right, what is this, a hard drive, I think. This hard drive spins through that number of degrees. So remember, one revolution will be 360 degrees. This is spinning so fast that it's covering not just one revolution, which is 360 degrees, but several revolutions, which works out to 43,200 degrees. So really what we're saying is, how many degrees have you revolved through, that have you spun through in 1 second? And in this case, it's 43,200 degrees per second. In the second one, the angular velocity, so angular means how many angles have you revolved through, measured in terms of radians this time, is 240 pi radians per second. Does that answer make sense now, Quinn? It's how many degrees you have spun through. Okay, okay, good. Okay, so Hussein is asking, how would the calculation change if it said radians per minute or per hour? Okay, great question. Well, in that case, I wouldn't be dividing by 60 in that case. I would just simply divide by 1 because I know that the answer, the question they gave me, all right, let me just repeat that question that Hussein is asking. How would the calculation change if it said radians per minute or radians per hour? If it was per minute, then this was given already in terms of revolutions per minute. I would just divide by 1. Now, if it was per hour, now I'm going to have to divide, I'm going to have to convert that minute into an hour, which means I'd be taking 1, right, that 1 minute, and dividing it by 60. So, okay, you know what? Let me just answer that question by doing the following then. Okay, hang on 1 second. All right, let's finish this first. Let's just finish this first. Let's put this in terms of, I think they asked for the answer. We can leave it at that. Doesn't matter. We'll leave it as it is. Angular velocity in radians per second. We'll leave it in as a multiple of pi, 240 radians per second. But I find the question, okay, Alexander, go ahead. Asking for a hall pass. Hussein, I like that question. I like that question. Asking how this would change. So let me show you how it would change. If this was asking about radians per minute, which is also angular velocity, then I would say that the answer would just be 7,200. So this is in radians per minute. Oh, hold on. Radians per minute. I would take the 7,200, multiply it by the 2 pi, and I would just divide it by 1 because it's 1. This was done in 1 minute, right? And that would be the end of the question. Whatever, what is that? 144,000 pi. Okay. But if this were, Kevin, I'm going to get to you in just a minute. But if this were per hour, now remember, in an hour, you're going to do a lot more revolutions because you have a whole hour to do it. So if this was radians per hour, then I would take that 1 minute and I'd have to convert it into an hour. Remember, 1 minute is 1/60th of an hour. So I would take 7,200 times 2 pi divided by 1/60. Right? That turns it into an hour. So this unit at the bottom is 1/60th of an hour. And how would I do that calculation? It would look like this. It would be 7,200 times 2 pi times the reciprocal of 1/60, which is 60, and that would work out to be, whatever that works out to be, some really, really huge number. right? That's how many radians it would have revolved through in a whole hour. Remember, we're just looking at this thing for a minute, right? So in a minute, it's going to do less than it would do in an hour, right? So it's going to do 60 times more in an hour because there's 60 minutes in an hour, if that makes sense. 60 minutes in an hour? Yeah, 60 minutes, right. Okay, so let me go back and just make sure Hussein is clear on that. Hussein, does that make sense? And I'll take Kelvin after that. Hussein, does that make sense? Does that answer make sense to you? Okay, perfect. And Kevin, can you just do a basic unit conversion? When you say a basic unit conversion, you're talking about going back to the original question, which was, let me see, I think I understand what you're saying. Take this 43,200 degrees and turn that into, get rid of the pi, so it would be 7,000 times. So like, for example, for radians per second, we would have to somehow get rid of the R, the minute unit. So we would be 7,200 times minutes over seconds times 2 pi R. Yeah, well, that's kind of, yeah, well, we kind of did that because we converted it, we converted the minutes, sorry, into seconds, and that's 60 of them. We take the answer the radius to minutes and times it by 60. Yeah, that's what we're saying, right? That's exactly what we're saying. In fact, that's what I just showed down here. It would be the equivalent of multiplying it by 60, right? To make it to an hour, if that's what you're asking. Good answer the radius to minute times it by 60. Yes. Hope I'm answering your question correctly. And again, if you just want to, speak out loud, and so you can, if you want to clarify your answer, your question that way, I'm happy to do that. Okay. All right. So Kelvin, are you good with what you were asking? Radians per second. Okay. All right. Okay. So guess what, folks? That is, yes, Queen. Go ahead, please. Mm-hmm. Mm-hmm. Yep. 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 Okay. Remember, so let me just repeat your question. You understand that it will be a lot more radians that you're going to be covering because it's a longer time. So when I chose to divide, what I'm first of all doing is changing the unit from minute to an hour, right? So to do that, I'm going to be changing it by saying 1 over 60. Why am I doing that? Because 1 minute is 60, sorry, 1 minute is 1/60th of an hour. Now, remember this, Quinn, when you have a fraction, let's just take let's just take a fraction here. If I have a fraction of 5 over 7, and I want to divide that by 2 over 3, which is essentially what we're doing here. So think about it this way. 5 over 7, and I'm dividing that by 2 over 3. The way that I do that is I can take the top, which is the 5 over 7, and I multiply it by the reciprocal of the bottom, which is 3 over 2. All right? That's how you divide by a fraction, by multiplying by its reciprocal. So that's really what we're saying here. All right? Okay. All right. Okay. So guess what, folks? I have actually just finished what I had planned to do for radians and degrees. Your homework tonight, and there is homework tonight as well. So there is the assignment, and that's not due until next week, Monday. But there's also homework, and the homework is actually going to be based on the stuff I'm about to do next. So remember, I'm going to be running into the second block 2 period with this. I will stop at the usual 11:15, give you a 5-minute break. Those who want to step away and not come back, you're fine because I'm not doing attendance after that. But that will be part of the recording that I will put online later on. Okay? So, or maybe I should just take the break now. Maybe that's what we should do because I'm about to start looking at what are called special angles. There's 11:01 now. I'll stop this recording, right? And then at 11:06, let's say 11:07, I'll give you 1 minute extra. At 11:07, I will start again. Where can we find recording? So what I'm going to do, Synduja, is in the calendar, I'll put a link each day to whatever the recording is for that day. It will be a YouTube recording, but so you look for on today's calendar, the 4th of, what is this? The 5th, I guess, the 5th of January, and you'll see a link there that takes you to the recording for that day. So that's what we're going to do. I might just put the two together because I can edit the video, or maybe I'll make it two separate videos. I don't know yet. We'll see. But that's how I'm going to be doing this. Let me let you take your break now while I stop this recording, and we'll come back again and we'll go into the stuff on special angles. All right. So again, those who choose to not come back for that, that's entirely your call because I'm not doing attendance again, but that's how we're going to be doing it. Okay. All right. So I'm going to stop the recording now. I'm going to put myself on mute.